We are covering single degree of freedom vibration for the FE civil exam. This topic is found in the Dynamics chapter of your NCEES FE Reference Handbook. The most fundamental concept is the undamped, free vibration of a simple spring mass system. The key parameter is the natural circular frequency, omega n, calculated as the square root of k divided by m, where k is the spring stiffness and m is the mass. A major exam trap is units. In U.S. customary units, you're often given a weight in pounds. You must convert this to mass in slugs by dividing by gravity, 32.2 feet per second squared. Stiffness K should be in pounds per foot. Let's take an exam-style problem. A 20,000-pound water tank is supported by a structure with a lateral stiffness of 40,000 pounds per foot. To find the natural circular frequency, first calculate the mass. 20,000 pounds divided by 32.2 feet per second squared is 621.1 slugs. Then, omega n is the square root of 40,000 divided by 621.1, which equals 8.02 radians per second. The exam may ask for the natural period, t, in seconds, or the natural frequency, f, in hertz. Don't confuse these. The period t is 2 pi divided by omega n. The frequency, f, is simply 1 over the period t. So for our example, the period t is 2 pi divided by 8.02, which is about 0.78 seconds. Now let's introduce damping, which is the dissipation of energy. In the real world, systems don't oscillate forever. This is quantified by the damping ratio, zeta. Zeta is the ratio of the actual damping coefficient, C, to the critical damping coefficient, C sub C. The handbook gives you the formula for the critical damping coefficient. C sub C equals 2 times the square root of K times M. The value of zeta tells you everything about how the system behaves. There are 3 cases you must know for the exam. Case 1 is an underdamped system, where zeta is less than 1. This system will oscillate back and forth with decreasing amplitude until it settles at equilibrium. This is the most common case for structural vibrations. Case 2 is a critically damped system, where zeta equals exactly 1. This system returns to equilibrium in the fastest possible time without any oscillation. Think of a perfectly designed automatic door closer. Case 3 is an overdamped system, where zeta is greater than 1. This system also returns to equilibrium without oscillating, but it does so much more slowly than a critically damped system. A common exam question will give you M, K, and C and ask you to classify the system. You'll calculate C sub C, then find zeta, and compare it to 1. Another question style might show you a graph of displacement versus time and ask you to identify the damping type. If you see oscillations, it's underdamped. If it returns to 0 without crossing the axis, it's either critical or overdamped. To remember this, use this mnemonic. Zeta less than 1, oscillation has begun. Zeta equals 1, returns on the run. Zeta over 1, return is overdone. This simple phrase can save you valuable time on the exam. For free practice questions, AI-powered explanations, and more exam prep tools, visit openexamprep.com. That's openexamprep, all one word, .com.